So guys, titrations, we use them in chemistry a lot. Okay, so in labs all across the country and the world, they will perform titrations, and what it allows them to do is it allows them to find the strength of an unknown solution. So when I was working at Kodak, my internship, this was years ago now, they were doing titrations as one of their tests on a product to make sure that the product that they were making was up to the standards of what they said that it was this concentration of something, so they would perform a test titration when they'd make a new batch to see, okay, did it actually meet the criteria of what they're advertising, what they're selling it as. Okay, that's where they come in. So they have an unknown solution or something, or they're trying to test out a solution to make sure it meets certain criteria, and then they can see, okay, based on how much of something else they're titrating with. So you take an acid or a base, whether your unknown is a base or it's an acid, guys, you will titrate using the known of the other. Does that make sense? So if you're looking for the unknown concentration of an acid, you're going to titrate using a base. Okay, and what we're doing in a titration, folks, is we're trying to get to what's called the equivalence point. All right, what do you think equivalence point means? Equal, right? Because it sounds like, what's equal? Josh? Okay, so pH and pOH are going to be equal now. But what does that even mean, though, guys? pOH and pH are both related to what? Yeah, concentration of what? Yeah, the two ions, right? So, guys, the equivalence point is where your H plus concentration equals your hydroxide concentration. All right? It's where those two ions are equal, where you have the exact same amount. So if you have 5 ions of hydrogen ions, you're going to have 5 hydroxide ions to make it equal. Notice the curve that we see in a titration graph. Okay? We can see that, for a while here, going along, right, it's kind of flat, and then all of a sudden it gets to a point where it shoots up very straight, and then it levels out again as you add volume. And this is what a titration is, folks. It's very, very precise at a very, very accurate piece in time or point in time with an amount of volume. Okay? So what you're doing, I'm going to show you an example here in just a minute of what's happening, is you're going to have an unknown solution. Okay? You know the volume of your solution, but you don't know the molarity. That's what you're going to be figuring out by performing a titration. This is where stoichiometry comes into play. We're going to be using what are called neutralization reactions. What's a neutralization reaction? What do they always produce? This is review from the last unit. Salt and water. Okay, they always produce a salt and water. Now, what we're going to use with our titration on Friday in the lab, we're going to have a strong acid and a strong base. So the equivalence point should be, right around 7. Right? It's going to get that salt water. Now, doesn't mean you have to always use a strong acid and a strong base, because you're not always going to. Notice, guys, with a strong acid and a strong base here, where's the equivalence point at? About 7, right? That should make sense because that's neutral. If we're doing a neutralization reaction, we should produce about a 7 pH. That's neutral. That's in the middle of our pH scale. But if we switch it up, and let's say we have a weak acid and a strong base, our equivalence point will shift. Notice where it shifts. It shifts to where? Yeah, above 7, right? More basic. And if we have a strong acid with a weak base, where does it shift? Below 7. So it's going to shift. Your equivalence point will shift based on the type of substance you have. Okay? Now, those of you taking AP, you will talk more about these weak acids and weak bases, and what those will do. There are other types of titrations as well, where you have a polyprotic acid, where you have a diprotic or triprotic. How do we know if it's poly or if it's a polyprotic acid? Poly means what? Many. So many what? Protons, okay? You're going to have multiple ionizable protons, which is going to lose more than one. That goes back to our review of conjugate acids and bases, which we will start to do for our test next week, because you will see those again, just like before break. But folks, those polyprotics, they will have a couple equivalence points, where their graphs may look something like this. And they have 2 where they go up like that. In this class, we're not going to worry about that. But those of you taking AP next year, you will talk about these weak acids and weak base titrations. You will talk about multiple equivalence points with the polyprotics. All right, but we will stick in this class with just the strong acid and strong base, kind of the most, no pun intended, basic problems. All right. the simplest problems that we're looking at. I said no pun. I wasn't even trying to make a joke there. It just happened to be that way. What's that? I know, but what have went over most of your guys' heads? So, anyway. I didn't say that. I did not say that. All right? You guys were just too focused. That's what it was. So, when you go through and you start calculating a titration problem, folks, it's a process. You've got to know the steps for that. Just like most every other thing in this class, if you follow the process, it's going to be a whole lot easier. 4 steps. First step, we got to use our balanced equation. What does it say in red on mine? You may have to write it yourself. I may only give you reactants. You have to write the products, balance the equation, and go from there. So you've always got to make sure that you have a balanced equation. If it's not balanced, folks, you're not going to be able to get anywhere at all. All right? Neutralization reaction. So if it's a neutralization reaction, what is always produced? Salt and water. So you know, if you have to predict products, guys, that water is going to be one of your products. What's the state of matter for that? Liquid. All right, and the salt is going to be what state of matter? Aqueous. The salt, guys, is going to be aqueous because we said that group 1 and 2 salts are always aqueous. All right, group 1 and 2 salts are always aqueous, which is what you're going to have there. I would not give you a salt of like a transition though. Right? It just doesn't happen that way very often. All right, so that's step 1 is know your reaction. Number 2, we got to determine the moles of standard solution. That's a key word there, guys. Standard solution. All right, you should be jotting the notes down that I make as well. Standard solution, guys, that's your known solution. Okay? When you hear that term standard, that means it's your known. All right? You know what that is. It's been standardized. Okay? Now, it may be an acid in one problem. It could be a base in the next one. All right? So it depends on what you're looking for. All right? So we're going to determine the number of moles of that used during the titration. Then, based on our neutralization reaction, we're going to figure out the number of moles of unknown solution, and then we can determine the molarity. Because what's our formula for molarity? Moles over what? Volume. And what is our unit for volume? In molarity? Liters. Moles per liter, folks. So, we can determine the molarity, guys, and calculate the unknown concentration because what we're going to be solving for using the titration, it's going to be based on the molarity of our base and how much we use. That equivalence point. When we get to the equivalence point, we know that the concentration, meaning the number of moles of hydrogen ion and hydroxide ions are equal. That equivalence point, guys, means moles of your base equal moles of your acid. So when you're at that equivalence point, okay, when you're at the equivalence point, you know, or you can use that equation, your reaction, your balanced equation, to figure out the moles of your acid or your base, which is your unknown. All right, so when they're at that equivalence point, the moles of your base equal the moles of your acid. Meaning, again, like we said on the slide before, hydrogen concentration equals hydroxide concentration. Does that make sense? That's kind of the theory behind it. Now, the math that's involved, folks, you've got to be organized. All right, this is the one problem more than anything else this year, that if you're not organized with it, you're going to just be completely off. Okay? And you'll notice, if you flip to the next page in your notes, you're going to have a setup like this. Okay? So it's a big box that you're going to want to keep track of everything. Now, folks, if you don't have space on your note page, you can, 1, print out the full pages, or 2, you can jot them down in your notebook, kind of the same chart, so you have enough space. But this is what it's going to look like. This is set up. So you've got acid data and you have base data. Each problem is going to differ, which is your unknown. So the biggest thing is we're going to have to go through and we're going to have to figure out, all right, which is which. Okay, which is which. So here we go. Let's start going through this. So it says, in a titration, 27.4 mils of a standard solution of, what's the name of BaOH2? barium hydroxide, is added to 20.0 mils of what's HCl? Hydrochloric acid. It says the concentration of barium hydroxide is 0.0154 molar. What is the molarity of HCl? So, let me ask you this question. What's my unknown solution? HCl. Okay, so I'm looking for the molarity of my HCl. So I'm going to put a question mark right here. That's what I'm looking for. Every other of the three other four pieces I'm going to have the information for. What's my volume for my acid? Nope. 20.0 mils. Now notice, what does it say right here, folks? Volume has to be in liters. So go ahead and do that conversion right away. How do I go from mils to liters? Divide by 1,000. So when I divide by 1,000, what does that equal? Got to keep the other numbers there as well, folks, because they are significant. So sig figs do play a part in these calculations. So you have to have the zeros after the 2 there, because you had 3 sig figs in your original number right here. You've got to keep those same 3 sig figs right there. What's that? Oh yeah, it should be liters right there. My bad. All right. So all we're doing right now is we're just jotting down our information. Now the base. My base is barium hydroxide. What's my molarity of my base? This is where it becomes crucial, guys, that you know your units. What does capital M equal? N over V, or moles per liter. Moles per liter. N does mean moles, but make sure V, guys, it's talking about liters. What's the volume of my base? Yeah, 0.0274 what? Liters. Have I done anything crazy yet? All I've done, guys, is write down my information. Okay? The only conversion I've done is go from milliliters to liters, which should be a piece of cake at this point in the year. Now, go back and look at your notes. What does step 1 say? What is step 1? Write a balanced equation. So, guys, where it says write the balanced equation, you need to go through and do that right now. What are my reactants? What's one of my reactants? HCl plus what? BaOH2. Now, make sure, guys, your balanced equation has to have 3 things. What? That it is balanced. You got to predict the products. And what does it have to have? States of matter. From the rest of the school year, like we said, it has to have states of matter, so your solubility rules will come in play. Go ahead and predict your products and balance your equation right now. So, it's a neutralization reaction. Yeah, that's a big giant arrow. I'm going to, I don't want to write over the words. Okay? So, neutralization reaction means what is one of your products always going to be? Water. So you know that water is one of them. What's the state of matter going to be for water? Liquid. Okay, H2O. And what's my other one going to be? BaCl2. BaCl2. Crisscross method. Barium's got a 2+ charge. Now, for the sake of balancing, folks, you may want to write water as HOH. It'll be a little bit easier to balance. When you balance this equation, all right, we should have a 2 in front of the HCl and a 2 in front of water. Correct? All right. Any questions about that? That should be a piece of cake. All right. Step 1, balance the equation, predict the products. We did that. What does step 2 say? What does step 2 say in your notes? All right. Determine the number of moles of our standard solution. Which is my standard solution here, my acid or my base? Why is it the base? Because we know the concentration, guys. Standard solution means you know that. So, we have molarity. We have volume. Is there a way that I can solve for the number of moles? Well, what's my molarity formula, guys? N over V, or L, right? Because it's in liters, same thing, it means volume. We got to solve that. How do I get N by itself? Multiply. Guys, cross multiply here. So really it's just going to be N equals molarity times volume. So what's my molarity here? Well, I'm going to write it down here where I got a little bit more space. 0.0154 moles per liter times, this is why we have to have our volume in liters, because we're multiplying by molarity. It's going to be 0.0274 liters. Liters are going to cancel out. Do that math, guys, to show me how many moles of my base I have. Anybody? No, it does not need to be in scientific notation. It can be, doesn't matter. What did you say? Now, don't round, folks. Go to a few non-zero decimals. All right, so 0.00 4219. So 4219 is fine. Okay, 422. If you had as 422, guys, that's going to be fine as well. We just can't have just one non-zero decimal. If you round too soon, guys, your final concentration will be off. All right, so you've got to go to 3 or 4 non-zero decimals. That's why I've gone out like that. All right, so there's my moles. What's my next step? We figured out the number of moles. My next step is to?
Determine the mole solute solution.
Right, so now we're going to figure out the moles of our unknown. Well, to go from moles of one substance to another, guys, what do I need? Mole ratio. So if we take a look here, so we're trying to go from, I'm going to highlight it, we're trying to go from this to this. We need to figure that out. So that's our mole ratio we're looking at, guys. We won't use our products in these mole ratios here. So, what's our mole ratio? 1 to 2 or 2 to 1, depending on how it is. Really, guys, what you would write in the mole ratio portion is 2 moles of HCl to 1 mole of BaOH2. And I wrote that wrong up here. You can go back and erase that. It's OH2 like that. Okay, so now we're going to do our mole conversion, guys. We're going from given to unknown. So my given is going to be that 0.0004219 moles of BaOH2. And now I'm going to go to HCl. Well, this is review. 1 mole of BaOH2 on the bottom. We have 2 moles of HCl on the top. So how many moles of HCl will we actually have? What's 4 times 2? 8. 2 times 2 is? And 1 times 2 is? All right, so 2. And it'll be something else. So really, guys, it's going to be like 4, 4. That's how many you would have. How many moles of HCl? Now, how do I figure out the molarity, guys? Yeah, N over V. Right? We have the V already. We have our moles. 0.000844 moles divided by our liters, which we already did at the top, 0.0200 liters. So the molarity of our unknown acid, go ahead and do the math. What do we get? 0.0422 molar, guys. HCl.